So this is lecture 21, and we continue our discussion about irreducible decomposition. So definition. So now we want to slowly shift to discussing irreducible decompositions of ideals as opposed to spectrum of a ring. The reason is that if you have to work with arbitrary rings, we need this notion and not just for spectrum. One important reason is that we have not yet defined it, but we will come to it. The irreducible decomposition of an ideal and irreducible decomposition of its radical would be different, but the spectra are the same. Okay, so there, if you take the reducible decomposition, it's going to be it will be the same. Okay, so let R be a ring, and I an ideal. Okay. Say that I is irreducible. If there does not exist R ideals I1 and I2 such that I is a proper subset of I1, I is a proper subset of I2, and I is the intersection of these two. So this is a non-trivial intersection. So I equals I1, I intersect I2 is a non-trivial intersection. Okay. And if there is no such decomposition of I, then we say that I is irreducible. Sorry, we are just defining this term. I is reducible if there does not exist such a decomposition. So this is an important notion. It sort of generalizes the notion that we just talked for spec. So here is a proposition. Let R be a Noetherian ring and I an R ideal. Then there exist irreducible ideals J1, so finitely many irreducible ideals Jm such that I is the intersection of them. So any ideal can be written as a finite intersection of irreducible ideals in an Noetherian ring. Okay, so this is this proposition, and okay, so this we will use this as we'll prove this. We will use this as a starting point and try to get more understanding of this decomposition. And this will take us a few lectures, and it's going to be more abstract than what we have discussed so far, but and eventually after a while we'll come back to computational aspects of this question. Okay. How do we try to find this decomposition? Okay. So the proof is sort of a typical proof in an Noetherian case. Okay. So suppose this is not true. Suppose I cannot be written that way. Suppose I does not have such a decomposition. Okay. What does that mean? Well, I cannot be written as a finite intersection of irreducible ideals. In particular, I is not irreducible. irreducible ideals themselves can be written as just I equals I. Okay, so that would satisfy them. Okay. Therefore, there exists some I1 and some I1 prime such that I is I1 intersect I1 prime and I is not equal to I1, I is not equal to I1 prime. Okay, so these are strictly bigger ideals which contain I, but their intersection is I. Now the proposition cannot hold for either one of these, because if the proposition cannot hold for one of these. Suppose the proposition holds for both, then this is an intersection of finitely many irreducibles, this is an intersection of finitely many irreducibles, and one can just put them together, and that is a finite intersection of irreducibles. Okay? So without loss of generality, the proposition fails for I1. Okay, that's not very. So it is just whatever we just discussed. If the proposition holds for both, it will also hold for an intersection. Because an intersection of two finite intersections is a finite intersection. Okay? So, and then without loss of generality, it's I1. And now we can ask, I1 can be written as some I2 intersect some I2 prime, where again I1 is not equal to I2. So it's the same reason, I1 is not irreducible because of this. I1 is not equal to I2 prime, okay, but their intersection is I1. So same argument, and again without loss of generality. The proposition does not hold. For I2. Thus we get a chain I1 strictly inside I2, strictly inside I3, and so on. Okay, but this is not, which is not possible in an Ethereum ring. Okay. Another way to argue using, so we had some three equivalence conditions for an Ethereum ring. Among all such ideals, pick one that is maximal, then same way it is not irreducible, so it can be written like this, but these are strictly bigger, so the proposition therefore will work for them, and that's one way of proving it. So among the three equivalence, among the two conditions that are equivalent to ideal being finitely generated, one can use either one of them to prove this. Okay, so now, as I mentioned, what we are going to work is to understand what this decomposition looks like. How do we determine this? What extra properties do these ideals Ji have? And how unique is it? And so on. Okay. So let's quickly look at it in Z, okay, or any Z or Kx or something. So let's look at an example. If you take R to be Z and I to be some prime ideals, let's say, I to be generated by some every ideal is principal, so I to be generated by some n, where n is some P1 to the E1 up to some PR to the ER, Pi is prime, so let's say EIs are positive, and Pi different from Pj if I is different from J. Okay, so we have this. Then what is the prime? What is the irreducible decomposition? Then so one needs to check this a little bit, but after we discuss all these things, it will become clear that this is I is P1 to the E1 intersect P2 to the E2 intersect up to PR to the ER. Okay, the point. So it is easy to check that. So n is in all these ideals. So n is divisible by this, by this, by this, etc. and by no higher powers. So that's just for unique factorization. One would get this equality of this I equals this one. What one needs to check is that these ideals are irreducible, but that again one can write out explicitly, saying if P is a prime and P to the E is some J1 intersect J2, then one of them must be equal. Okay? So this is an example. Okay. So we would like to understand, extend this to higher various other rings, larger number of variables, abstract rings, etc. Okay. Okay. So first of all, we'll have to switch to the language of modules at this point. Okay. And we'll have to introduce some notation, some new language, etc. Okay. Definition. Let M be an R module. Say that P, a prime ideal P, is associated to M if P equals the annihilator. So I'll define, I have not yet defined this, of X for some X in M. Okay, so we just need to define what this is. So a small discussion. So M is an R module, so this is a discussion, and we'll come back to that. Okay. Yeah. Okay. So now so R is a ring, and N inside M R module. N is a submodule of R modules. Okay, so M is a submodule and N is an R submodule. Okay. Let X be inside M. Okay. Then we define the following. We write N and we put a colon, subscript R, X. Okay. We write this to mean, so this by definition, okay, so all the elements are in R such that, so here is this is the set from where the elements will come, and what it does, Rx is inside M. Okay, so this is read as N colon X, and if you want to be specific, N colon X over R. Okay, so this is a notation. Okay, so this is a yeah. So now it's easy to check that this is an ideal of. So these are all the elements in R that multiply X into N, and one can observe that this is an ideal, and that ideal is a proper ideal if and only if X is not inside N. If X is inside N, then 1 will belong to the set, so it will be all of the ring, and if X is not inside N, 1 cannot belong to this set, so it is a proper ideal. Okay, so this is an ideal. One can extend this to also a subset of extend to a subset X of M, not necessarily a submodule. So we can write N colon X over R. This is a set. So this is the set of R in R such that Rx is inside N for all X in X. And it is then easy to see that this condition is to impose this condition on every X. So this is the same thing as n colon x over r, x in x. Okay. So this is just an observation. We can, so underlying thing is we have to get this multiplication. Okay. Now, so we can also reverse the role of r and m in this case. Okay. We can ask for a inside r, we can write n colon a, but now it would be over m, and that is just elements x in m such that ax is inside n. So these are the elements of m that multiply a into n. Okay. So this is a R submodule of m. Okay. M is a bigger module, R submodule of m, and elements of n. So if x is inside n, then ax is also inside n. So this containing n. Okay. And we can also do this for an arbitrary subset. Okay. So I will not write it. It is the same idea to a subset A of R. Okay. So then we can write n colon A of R defined as like this. This is the intersection of n colon little a. Sorry, this is over m. Okay. So we can so this is just multiplying, and this is just what multiplies some element to a subset. Okay. So then annihilator of x in R is just precisely 0 colon x in R. That's what we meant. Okay. So that is, this is the set of all R in R such that Rx is 0. Okay. So the reason why we introduce the colon notation more than just writing annihilator is that quite often we will have to work with things of this kind. Okay. N colon some other submodule, quite often this x will also be a submodule. So n colon some subset over R, or one of these like this. So, which is the reason why we introduce this notation. It's just notation, not nothing much. I mean, we will need this later, but okay. So that explains what annihilator is. This is just this annihilator, and yeah, one more piece of notation, definition or notation. We denote the set of associated primes by associated primes of M by as M. Okay. So one observation about associated primes, or in general about annihilators, remark. Let x be inside M and I the annihilator of M, annihilator of x. We observe that annihilator is an ideal. Okay. Then the map, the R linear map R to M, given any R module and an element inside the module, there is a natural R linear map which takes 1 to that element. Induces, so this element induces an R linear map So this is a map from R mod the annihilator, which is I, to M, an injective map to M. again 1 bar here will go to one bar here will go to X. Okay. So what we are really saying is that there is the map from R to M, and then there is a natural quotienting map, and then 1 goes to X here, and from here 1 bar goes to X. Okay. So in other words, we say that this arrow is a composite of these two arrows. Okay. So this is what this is an observation. Conversely, if there exists an R linear injective map R mod I to M, 1 bar goes to X, then I is the annihilator of X. Injective. This is the point here is injective. Okay. So we said that. Okay. So why did we say all these things? We were discussing associated primes, and what was the definition of associated primes? Say that P is an associated prime if P is the annihilator of R mod M, of some X inside inside M, and that, so now we can rewrite now. So now therefore P is associated to M if and only if there exists an injective R linear map from R mod P to M. Okay. And quite often this is how we probably use it. Okay. So this is what we mean by an associated prime. Okay. And yeah, so remember, we are trying to make sense of or try to refine the idea of an irreducible decomposition, and we are sort of slowly progressing towards it. So now, how do we know that a ring has, a module has associated primes, or do modules have associated primes? So that's not, in general, it's not very easy to answer, so, but here is one proposition. So right now R is just a ring, and M an R module. Okay. Let I be maximal among the set annihilator of X, so in R, so it's an ideal of R, such that X is inside M, X is inside M, X is non-zero. Okay. If you put X 0, then the annihilator is a full ring, and we don't want that in the set, because then that will automatically be the maximal. So proper annihilators of non-zero elements, so they are all proper ideals, and I be maximal among these things. Then I is prime is a prime ideal, and hence associated to, if it's a prime ideal with this property, then it is an associated prime. Okay. So this is one way of proving, one way of looking for associated primes, but but of course this is not guaranteed that such sets will have maximal elements, except therefore in particular if R is Noetherian, then it's non-empty. Associated prime, the set of associated primes is non-empty. Okay. So modules over Noetherian rings have associated primes. Okay, proof. So the last part is just an immediate consequence that any set of non-empty collection of ideals have a maximal element. That's a property of Noetherian rings. So the last part is immediate from the first part itself. So we'll just prove the first part. Okay. And the last part is immediate from the first part because R is a Noetherian. So we'll just prove the first part. Okay. Okay. So let Rs be inside R, the product inside I, and S not inside I. So we want to show that R is inside I. Okay. So what does that say? So the product Rs x0, because Rs is the annihilator of x, but Sx is not 0, because S is not in the annihilator. That's just rewriting this condition. So we want to consider the annihilator of the element Sx. Okay. This contains I. Why? Because for all A inside I, A times Sx is same thing as S times Ax, but A is the annihilator of x. So remember, this is the annihilator of x. So this is 0. Okay. But I is maximal in that family of annihilators of elements. Maximality of I implies that I is equal to that. So this is equal to this. But on the other hand, by the same property, R times Sx is also 0, right? Because Rs is in the ideal, since Rs is inside I. Okay. So R times Sx is 0 since R is inside I. Okay. So then this now implies that, so let's just go back. It now implies that this set here contains R, but that's also equal to I. Okay. So now this implies that R, which is inside annihilator of Sx, which is equal to I. Okay. And yeah, so now therefore I is prime. Okay. And therefore, by definition of what an associated prime is, any prime ideal which is an annihilator of some element is what is called an associated prime. So therefore, I is in associated. Okay. And if R is an Noetherian, that family of ideals is non-empty. Therefore, it has a maximal element, and therefore those are associated primes. Okay. So this is the end of this proposition.